Today, we're going to review the major reproductive hormones in both our AMAB and AFAB populations. We'll look at how these hormones are produced, how they're regulated by hypothalamic pituitary gonadal axis, and the clinical implications when these systems malfunction. This lecture will also tie in pathologies like hypogonadism, PCOS, and prostate cancer screening so that you can understand how these hormone patterns present in real clinical practice. Sex hormones are steroid hormones, primarily synthesized by the gonads and to a lesser degree, the adrenal cortex. These hormones influence brain development, genital development, metabolism, and reproduction. The main categories are androgens, estrogen, and kind of cheese stands on its own, progesterone. It's important to remember that both AMAB and AFAB populations produce all three types. It's the relative levels that differ and create physiologic distinctions. During early development, sex hormones bind to receptors in specific brain regions, including the hypothalamus and amygdala. This shapes neural differentiation. The AFAB hypothalamus develops the ability to generate cyclical hormonal patterns, which is essential for ovulation. In contrast, the AMAB hypothalamus becomes tonic, meaning it lacks the cyclical rhythm. This fundamental difference underlies a lot of the structure that surrounds the menstrual cycle. Steroid hormone synthesis is governed by the hypothalamic pituitary axis. GnRH from the hypothalamus stimulates the anterior pituitary to release LH, luteinizing hormone, and FSH, follicle stimulating hormone. LH drives steroidogenesis, the production of testosterone and estrogen, while FSH supports gametogenesis. A classic negative feedback loop regulates the system as LH and FSH rise. They suppress upstream GnRH, and that helps to maintain hormonal balance. Now, throughout our life, gonadal function is not static. GnRH will essentially has a pulsatility, and our pituitary's responsiveness to that pulsatility and gonadal steroid production will all vary from fetal development through puberty, adulthood, and aging. Clinical evaluation of reproductive hormone levels must always take age and developmental stage into account. In AMAB physiology, LH and FSH have distinct roles. LH stimulates Leydig cells to synthesize testosterone, while FSH acts on Sertoli cells to support spermatogenesis. Inhibin B and activin, both produced by Sertoli cells, provide essential feedback. Inhibin suppresses FSH, while activin stimulates it. In clinical practice, inhibin B can be a useful marker of testicular function. GRNH secretion follows three rhythms: seasonal, circadian, and pulsatile. Seasonal variation affects testosterone peaks. Circadian rhythm produces the highest morning testosterone levels, and pulsatile secretion occurs every 90 to 120 minutes. Melatonin also influences this pathway as it can influence both seasonal and circadian components, leaking our reproductive hormone secretion to the body's internal clock. Testosterone provides negative feedback primarily at the level of the hypothalamus, and these kind of images show that. So we can see that through these three images here. Whereas estradiol produced via aromatization of testosterone feeds back more strongly at the pituitary gland. This distinction helps to explain the differences in LH versus FSH regulation. In AMAB individuals, LH is primarily controlled by high testosterone levels, while FSH is more influenced by estradiol. Looking then further, now that we kind of are seeing the different steroid feedback mechanisms, we can see these different kind of pulsatile rates through these images here. We can look specifically at our next stage, a kind of, well, what is actually happening with LH and our Leydig cells? Well, a core function of LH in AMAB physiology is stimulating our Leydig cells to produce testosterone. This is this cornerstone of male reproductive endocrinology. Any disruption in the signaling pathway at the hypothalamic, pituitary, or testicular level will directly impact testosterone production as well as fertility. Now, dihydrotestosterone, or DHT, is formed from testosterone via 5-alpha reductase in target tissues, such as the prostate as well as skin. It has a stronger androgenic effect than testosterone on its own, and it is responsible for development of external genitalia and secondary sex characteristics, things like body hair and male pattern baldness, for instance. Clinically, DHT is a major player in conditions like BPH, androgenic alopecia, and prostate pathology. Looking then further at testosterone, testosterone can be metabolized through two important pathways. First, aromatase converts testosterone to estradiol, which plays significant roles even in AMAB physiology, especially in bone health and pituitary feedback. Second, 5-alpha reductase converts testosterone to dihydrotestosterone, or DHT, which is a more potent androgen. These metabolic pathways help explain why disrupting enzymes like aromatase or 5-alpha reductase lead to major physiologic and clinical effects in the body. So, what does testosterone do? Testosterone influences every major component of AMAB physiology. It regulates fetal sexual differentiation, supports secondary sex characteristics, and is essential for spermatogenesis. It also plays major roles in muscle mass, bone density, and stimulating erythropoiesis, which is why low testosterone can contribute to anemia. Understanding these functions helps us interpret symptoms of hypogonadism. Now, over time, with aging, we see a predictable decline in testosterone levels. This starts around the age of 50 and above. LH levels rise because the pituitary has to work harder to stimulate the testes, but our LH pulsatility weakens. Leydig cells lose our sterinogenic capacity, and spermatogenesis becomes less efficient. Clinically, fertility will begin to decrease around age 40, and conception rates drop by roughly 50% compared to younger AMAB individuals. And this is kind of showing those changes with age and sexual activity in our AMAB individuals. Low testosterone can contribute to a number of metabolic disturbances, things like lower HDL, protective cholesterol, increased LDL, not protective cholesterol, impaired glucose metabolism, and even increased total body fat. The shift in lean to fat ratio predisposes individuals to further insulin resistance and cardiometabolic disease. It also accelerates bone loss, contributing to osteopenia or osteoporosis, and it can reduce total red blood cell mass, reinforcing why testosterone deficiency can present with fatigue or anemia and why it's a treatable condition. When we come back, we're going to specifically look at testosterone as a biomarker and some of its specialized components.